Welcome back to ECE 320A. We're in Unit 10, and this will be the last of our breaking down steps in terms of trying to break down the process of sketching Bode plots into fundamental steps so that we can then quickly, hopefully, add up those pieces as we move from low frequencies to high frequencies, from left to right, on both of the magnitude plot and the phase plot. Homework 10 is due at the end of this section. If you're looking for textbook material, that's in Appendix E. And this final video on breaking down the process is concerned with treating the quadratic terms. And in fact, what we are going to do is we're not going to focus or worry about the more detailed or accurate picture of these quadratic pieces. That varies as a function of the damping ratio. We simply want to focus on the straight line approximations, and for that reason we are approximating, and this is a big point to make. I don't know that I can emphasize this enough, but in this class we are approximating the shape of the magnitude and phase behavior associated with these quadratic terms in our Bode plot. Here is our motivation. Again, we're just trying to quickly sketch so that we can learn how to design with thinking about Bode plots, both in the magnitude plot and the phase plot. We're developing these strategies for minimum phase systems, which means that all of our poles and zeros are in the left half of the complex S-plane. And as I have already stated earlier in this video, we are at the bottom of our breaking down process of these individual terms. And in this video, what we want to focus on is the quadratic piece. And that piece could be either zero factors that are quadratic or pole factors that are quadratic. And zeros are in the numerator, those are upstairs. Things will break up. If they're zeros, they break down. If they're poles, we will focus in this video on the pole behavior, but you can essentially mirror that and do that in the positive slope directions for the zero factors, and you'll then know how to sketch quadratic zero factors. Let's then remind ourselves of how we're doing this, and a standard form that you might see a quadratic written in is illustrated here. S squared plus 2 zeta omega sub n s plus omega sub n squared. The zeta is the damping ratio, and that really influences the angle with which these quadratic pole factors or poles make with the real axis. Omega sub n is our natural frequency, and that's the distance we are in those poles away from the origin. We want to put that into time constant form, which means we want to normalize the constant coefficient to have a value of 1. We can do that by factoring that piece out. So in the next expression on the right, you can see that we factored omega sub n squared out from all three terms in that quadratic. In the middle piece, we've actually factored it, the omega sub n squared itself, in the denominator so that we can put one piece directly under the omega sub n and those go away, and we can put another omega sub n factor underneath the s. We can pull out the squaring on the s over omega sub n. We've squared the numerator and denominator in that first piece, and I've not worried about carrying down that omega sub n squared, the constant. That will be absorbed into the constant factor or constant term. So we want to just focus on this piece, which is the quadratic behavior associated with two complex conjugate poles, or two complex conjugate zeros. Here we are now in our standard form normalized. This is now our time constant form. This is what we want structure-wise in order to make these sketches in the Bode plot. And in this class, this is not the way to sketch necessarily a Bode plot for a quadratic factor, but it helps us quickly approximate this behavior in both magnitude and phase by simply saying, let's just rotate those complex poles down to the real axis and consider this quadratic factor to actually just be a pair or a set of repeated real poles that are a distance omega sub n. The natural frequency hasn't been changed. We're just rotating that in the complex plane, and that now allows us to quickly apply our linear or real pole steps in the Bode plot sketching process. We just have to double it because of the fact that this is now a quadratic, it's squared. So we are, in this class, going to approximate the quadratic term with two linear terms. If we return to our example that we've been using throughout this development of the individual terms, we now have, and hopefully if I ask you a question, you could immediately tell me where those factors or where the roots of this quadratic live. Hopefully if I say, okay, where are the locations of these complex, I just gave it away, where are the roots of this quadratic? Hopefully you then can see by inspection of the way that it's factored here that those values of s, minus 6 plus j8 and minus 6 minus j8, would actually make that quadratic expression vanish or equal to 0. If we now write it more multiplied out in a less factored form, we then have the s squared plus 12s plus 100. We factor out the 100. That's the natural frequency squared, and conveniently for us, 100 has a nice square root. So we now have s over 10 quantity squared plus 2, 6 over 10 times s over 10 plus 1. And what we want to do in this particular movement into this black approximation is we are actually saying that we are now letting zeta go to 1. And here is the zeta piece. In this case, we're saying go from 0.6 to 1, and that now allows us to approximate So this approximation step is allowing us to simplify the sketching of these quadratic factors. We're not worrying about bending those or influencing those relative to the damping ratio zeta, and you can look in the textbook and see how those now make the transition sharper as zeta moves from 1 back towards 0, or as zeta goes from 1, where you have purely real poles, towards zeta going to 0. Now, once zeta is equal to 0, you have purely imaginary poles. And those poles are still a distance omega sub n, or this natural frequency, away from the origin. It's just now they're on the imaginary axis. We want to rotate those all the way around to be on the negative real axis, a distance of omega sub n from the origin. Now we want to sketch this quadratic approximation, and we can quickly write down, so to sort of guide our thinking that we will be doing in our sketch, we know for small omega, it's that particular term approximates to be 1, and 1 in dB is simply 0. So we have 0 dB until we reach the break. That's our agreed upon transition between what's happening for low frequencies and what happens for high frequencies. So we're 0 dB, we're flat for this particular factor written in time constant form until we reach the break, and the break here is at 10 radians per second. At that point, we now change our approximation to have some sloping behavior. It's a pole factor in our example. So now we're going down. Our slope is down. For a linear term, we would have 20 dB per decade down, but since it's doubled and it's occurring at the same break frequency of 10, now after or beyond omega equal 10 radians per second, we're sloping at minus 40 dB per decade. That's all there is to sketching the magnitude plot, and I've already sketched that here. And in your drawing, you go, oh, I'm just going 0 dB until I hit my omega sub n, which was 10 in this case, and now I'm going down at a quicker slope. So if you wanted to, you could say, oh, I was 0 at 10. A decade from that, I'm going to be 40 dB down. So you could just draw a dot there, and now you have a way, if you have a ruler, of just putting your ruler down and connecting those dots, and now you have the component part of this individual term, its magnitude. This is now the magnitude in dB of this quadratic approximation. What happens in the phase? Again, we can focus on the three frequencies. We have the small frequency, which is a decade before. We have the large frequency, which is a decade beyond. And we have the sweet spot, which is right at the break frequency. Right at the break frequency, which is 10, we have 1 plus j. That has an angle of 45. We're doubling it because it's a quadratic, and because it's downstairs in this particular case, in this example, it's a negative exponent. So we now have two 45s, but those are negative 45. So we're at minus 90 at the sweet spot. And I like to just write those 3 points down. We know at a decade before the break frequency, or 0.1 times the natural frequency, which in this case is 1 radian per second, we are at 0 degrees. A decade beyond the break, or a factor of 10 times 10, we're at twice, because we have a quadratic, minus 90 because it was a pole. We're at minus 180. And in between, we're actually identically or exactly halfway between 0 and minus 180. We're at 2 times minus 45, right at the sweet spot, or the break frequency of 10 radians per second. And I like to now just sort of dot those points in, and I've already done that a little bit. Now I would say halfway between, or right at the break frequency, I'm going to be at minus 90. In my approximation, I'm 0 degrees until I reach that low frequency value of a decade before the break. Beyond a decade above the break, I'm going to be at my final angle, which is minus 180. And between those two extremes, I simply approximate that angle by this straight line. And this is a crude approximation. As zeta gets closer and closer to 0, the transition becomes sharper and sharper, and so the actual curve, so this is for a zeta that is approaching, let me say 0. At 0, it actually would be 0 degrees, and then it would quickly transition to minus 180. But here you can sort of see that as we move from, this is the line when zeta is equal to 1, from zeta equal 1 to zeta equal 0, we make that transition a little bit more steep near the break frequency, or the natural frequency, which in this case is 10. Hopefully that gives you now a feel for and a strategy for sketching these Bode plots for the way that we're approximating these quadratic factors. And that's what you need to be able to do to quickly think through what's happening in these Bode plots.